is I would take the categoricals. I would
think so. That
Okay.
doesn't sound familiar.
Let me start off with that one. I wanted to show you guys part of that. I think we might have skipped a couple of slides that I was intending for us to go to because I think we got ahead of them, and then I was wanting to go back.
Well, I, as not being a CS person, I find this quite challenging because not that I'm computer illiterate or anything,
It's challenging for everyone, so I just do.
but
I do have a very challenge.
the data sets in ISLR2 and MAS are very limited in their functionality from like lab to lab. I've spent most of the time, like a couple hours, going through each and every usable data set to determine, run it through R, look at the summary, try to pick the best one. And a lot of them, I think, just don't have enough data to really spit out a decent correlation or a decent mean. Like, if it's less than 80 rows, then it's hard to split that up and get a good test or train and test.
I'm with you. And you know, honestly, that's one of the challenges that was probably one of the earliest challenges of machine learning is the cost of engaging with, back in the day, large data sets, you couldn't really process them because you just didn't have the memory to work with that much data. So what we're actually seeing here, and as I said beforehand, some aspects of this class can be a little bit like historical retrospective in some senses, but my main objective here is to start off with doing something, that's relatively accessible because of the scale, but at the same time, I think I added MAS this year as a data set source. As I've gone through it a little bit more myself, I do realize the same thing you say, it can be a little limited. So what I will probably try to be doing for the data sets, some of the data sets in the future is sourcing stuff on Kaggle. There is this weird point that happens, and I'm not really sure exactly why it happened, but it did happen. Within data processing in general, we went from having data sets with thousands to tens of thousands of samples up to data sets that were tens of millions of samples, right? It was an epoch shift. It was a major sort of reflow of the way in which we were doing data processing. I would say a lot of it had to do with maybe the expansion of memory processes, but some of it had to do with changes the way in which the data was being worked through the system, right? So previously we said, well, we can increase the number of samples and it doesn't give us a ton of difference in terms of performance. But also, here's the other thing, it cost us X thousands of dollars to pay somebody to go and collect this data, right? So when a lot of the data collection processes became automated, both data collection and labeling became more automated, we started getting larger and larger data sets. They grew so fast that some of the historical data sets are like woefully tiny, you know, like cold day tiny, and then some of them are like way too big to manage.
Right.
And that's the reason why I said finding the sweet spot data in there somewhere is probably going to be me attempting to curate something from a large set and bring it down for you. Sometimes, like I said, I'm not going to make any excuses, but you know, I teach 3 different classes this semester, and when I try to change something in a class, it's always a risk that I either make it too hard or too easy, okay? So right now I would say I added something to this lab. I give you guys a couple of extra days on it. I want you to work as hard as you can to accomplish the goals that I've given, but not an unreasonable amount. Also, if you find that you're not coming up with what you think you expect out of it, talk to me about it. That way I can clarify my understanding of what I'm intending you guys to do and maybe redirect it for somebody else if that happens in the future.
Just read my conclusion. I put it all in the conclusion. all the hardships, all the successes,
Oh,
and
great, yeah, that's what I was looking for.
and all the answers to the questions that you ask.
Okay,
I just
so-
thought it was weird because my confusion matrix came up what I thought was backwards, but yet I got a good, well, it was over 60% accuracy on each of them. And actually the naive Bayes for the third part came up even
That's
higher.
not possible. So there's something was wrong there. You can't have 120%.
No.
Oh.
Each individual one, the
Oh.
first two, logistic and the linear, both
Okay.
came out at
Oh, I see,
62.5%. And then the naive Bayes, because I did that for the third part, came out at like 68.6 or something like that percent.
Naive Bayes will sometimes outperform logistic and linear discriminant. I would say that it's a little bit more rare. Usually the only time you really need to use naive Bayes is when the number of classes exceeds sort of the reasonable amount, or reasonable number that work well with logistic, which we don't talk about that a lot in here, but I will say that there is kind of an upper limit for linear discriminant analysis. Logistics upper limit is what? Binary, right? Linear discriminant analysis upper limit is somewhere in the neighborhood of about 5 to 7 classes. It really depends on what the data looks like. If it's sort of systematically separated, it's workable. But once you get 5 classes, and they start to overlap each other heavily in the dimensions they're working with, you end up with very, very small scores to be able to tell the difference between the clusters. So even at the level of LDA, it's still not, it's only going to be able to maximize that separation to a certain degree. Once it's maximized, then you find a certain balance. All right, so let's look at, we were previously looking at toward the end, classification utilizing multiple LDAs, right? So I didn't get to this slide with you guys because I skipped past it to get to something else in natural conversation. But I want to point this one out. This is a classic problem, and this is one of those circumstances in which I could say the number of samples is really not the issue. It's whether or not the samples do a good job of being representational of the data. We've talked about that idea of whether or not there's sufficient entropy within the data. Entropy is what they call an energetic notion. It's to say how much information is really being contained within the data space of an object. So let's look at 2 different things, and let's describe first what is the entropy of this object. Not very high, right? Let's think about it from the perspective of attempting to compress it as a JPEG. You guys have understand a little bit about the idea of image compression, right? So you have sides and lines, and it's relatively easy to be able to sort of say that if I make like a region here, I can say much the same through this region, right? I can say that it's basically repeated within that space. With no variations and high repetition, you can say this pattern repeated n times. That's usually a mechanism of compression. Now, if I have an object that looks like this, right, it's very hard to compress that. The reason why is because the fact that it doesn't have any regular edges, regular surfaces, and from a data standpoint, this contains a lot more information than this does, because the individual distinctions over regions describe more variation per unit. As it becomes more varied per unit, what do we end up with? More rich data space. So I'm going to need only a few of these if I want samples of them. If these are 2 populations of, let's say, organisms, right? We have one little square organism and we have one squiggle organism, right? How many of them am I going to need to describe the population? I'm probably going to need a lot more of these than I am of these, because these are very uniform. They tend to have fixed characteristics, and there's not a lot of variance within the pop. But over here, I might have a lot of variance within the population as a result of the internal shape characteristics. So an entropy assessment of this characteristics is saying how much total energy is needed to represent that particular data point, or what is the relative spread area over which that data can occur. as the variance within the data is increased, you need more and more samples to adequately describe it. If you remember back when we were talking about the curse of dimensionality, this is very much a curse of dimensionality issue. So when you're talking about data points and you're saying you don't feel like there's sufficient numbers of them, usually what you're running into is things that are either very ununiform or things that are highly uniform, and it's difficult to distinguish them as a result of their uniformity. However, we have an example here that's given to us within the domain of biological systems, and one of the areas being encountered here is actually one that we've kind of seen previously. This happens to be a three-dimensional graph that's put together based upon a set of toy data, right? But similar process with three classes, we're going to apply to something called Fisher's iris data. Now, Fisher worked with separability analysis within the computational space, and his process was to attempt to understand which features, which characteristics of a multi-featured system provided the greatest degree of separability. So Fisher also created a mechanism of data projection that's similar to the linear discriminant analysis, Fisher projection models, that is a measurement or metric of the relative spread or relative separability between groups of sampling. What we're looking at here is we're just going to look at 4 features that make up 4 predictors that we're going to attempt to use to classify 3 classes. We have three species of iris, a flower, right? We have setosa, that's the blue one, and then versicolor and virginica. Notice those both start with V's. The indication here that I have, at least according to what I've studied on this, which I've read a little bit about it, is that the versicolor and virginica, as a result of being sort of those V characteristics, are relationships to the structure of the plant somewhat, like they have a V shape to them. And then setosa is like a reference to another sort of shape, like a chevron kind of style, all right? I don't know as they're all named that way, but I know these 3 species have similarities in their appearance such that it actually makes it relatively difficult for someone who is not really highly educated in botany, right, in plant sciences, to tell the difference between them. We can actually note here, as a result of the way in which this data is shown up, that that is the case. Notice we have 150 samples for 3 classes with equal distributions, so we have 50 samples for each individual species. Now, our goal, why did it do that? Our goal is separability. Wow, it is messing with me today. Our goal is separability. So we say, what axis or what pair of information would I use to separate those 3 relative classes from each other, right? Setosa, virginica, versicolor. I have sepal, right? Sepal length and sepal width. And I have petal length and petal width. Petal is out the external portion of the flower. Sepal, the internal portion of the flower, just outside the anther stamen. It's an internal flower, external flower. Notice that petal length versus something like petal width has a pretty good degree of separability, right? Right here, these are reversal plots, but they have a good degree of separability. Now, not perfect. Note we still have, even if I drew the discriminant right here, right, I would still have problems where I would have some of the versicolor and virginica mixed together. Why am I stuck with that? Well, basically because of the fact that if I want to do it on just one pair of pieces of information, all I can do is compare them together in their base objective, okay? I know I'm going to have some mixture, but if I wanted to attempt to try to find a more ideal projection, I could perhaps put together a variety of different angles and use a linear discriminant for each one. So a linear discriminant could be utilized to do a multi-projection and actually create 2 new axes as a result of 2 or more new incidents, okay? So what I'm talking about here is, imagine that I have one plot of information, right? And I've got Setosa, Virginica, Versicolor, right? I've got, these are overlapped each other pretty well, and this one's closed off. Setosa, notice, Setosa is fairly separable here. If we look at it in terms of separability analysis, it's almost like impossible that it overlaps, right? It's adjacent, it's close, but it's not going to, it wouldn't be hard for us to draw a linear discriminant in here either, right? So we could draw a linear discriminant, we could draw a logistic discriminant, or any other kind of LDA projection analysis would work in that space. Now, high separability, not good for the logistic, right? So it probably wouldn't be the best in this case. But if I was to look at this and I say, all right, how do I do this with respect to the LDA? Well, I can't project it direct onto this flat surface. What I'm actually going to do is I'm going to pick a new axis to attempt to maximize separability, both the mu of each class, right? And then attempt to maximize the between class spread characteristics. So within class spread minimized, centered, and then between class spread maximized. And I'm going to do so for all three classes. I'm going to create this one projection on this axis that attempts to characterize that, right? This might be, what do I have up there? Petal length, right? And petal width. So that's my first projection. This is a new projection. This is LDA for petal length dot width, right? This is a new projection. This is a new axis that combines together the information that was previously present in those two axes. Then imagine that I have another projection, same thing here where I have Setosa, right, Virginica, and then Versicolor, V, E, and then Setosa. I might find that, let's say, this axis here is ideal for separability, right? Now I've created a new one. Let's say this is petal width versus sepal length, okay? It's a rough idea. I now have a second LDA, right? This is LDA 2, which is the petal width to sepal length. Okay, LDA 1, LDA 2. What I've done is I've taken two previous dimensions and I've created a singular in dimension that is the linear discriminant of, or linear discriminant projection of, those two previous dimensions as a singular dimension. This is a type of dimensionality reduction in that sense. The reason why I say it's a dimensionality reduction is because from those two features, I've now reprojected them onto a linear space as a density function, right? The density function generative from the creation of the data space. Now I'm going to show you guys what this might look like as a plot out, okay? Notice, I have not a LDA graph, but I have a projection plot with two different discriminants. What I've done here is I've taken this discriminant and this discriminant, and I've placed them such that I have one discriminant, LDA 1, and LDA 2, I think I'm actually flipping these, on this plot segment, right? And as a result, I'm going to combine together their likelihood scores and create discriminants for those spaces as a result of the likelihood score based upon the features that were projected from the discriminant as discriminant variables. So this is a combinational approach. I now have a 2D plot that attempts to imply the likelihood of being in each of the relevant classes based upon the center of the class, not from a perspective of a singular dimension, a density analysis, but a two-dimensional density analysis. Notice the dots in the center of each group representing the means of that cluster, and then the spread in both the horizontal and the vertical axis being relative to the spread or likelihood as estimated by the LDAs in the dimensions that those LDAs were projected in. So these density analysis actually become the data plots or the spreads relative to the data plots that are projected in this particular dimensional analysis. So now I have potentially three or four dimensions, right, worth of data that I've brought into a new two-dimensional plot in order to do the output classification. So does everybody track with what we're doing here as far as the score analysis? Now that you guys have done this, honestly, it makes a little bit more sense to you, I'm certain. But one of the things I want to say here is that we have looked at this from a perspective of saying that class clustering grouping, right? When we have K classes here, we only need 2 discriminants. We have 3 classes, we only need 2 discriminants. So as a result, this is the K minus 1 discriminant characteristic. Notice that the separability of the classes here is actually higher than any previous set, any previous cluster, right? The separability of the reprojections of both samples is actually a distillation of the information that was previously contained within these 4 pieces of information. I kept the best parts that I was interested in that provided the best descriptive characteristics of the data points and then reassembled them into a new projection analysis that I could create 2 discriminants from, okay? I said I don't need to create the discriminants. Delta is based upon the pi and f, right? The pi and f, the prior and the prior, but that's the information state and the density function estimate. So if each delta is based upon the density function estimate and the priors, then I'm going to use 2 different density function estimates to create a new understanding of the space, such that I now create 2 deltas in this plot, in this space, which is in fact now a second tier derivative from the original data points. So you have the original data points, you have plots that create them, then you combine those 2 discriminant plots together, and now you utilize that data in order to create your discriminants. So you're making an estimate of the class based upon an estimate of the density based upon an estimate of the original data points. It's 2 tiers back from the original data. It's really pretty fascinating in my opinion that you can kind of get so obfuscated from what's actually happening under the surface and get something that functions or is functional. So this is all I really want to show you from 4. I don't think there's anything any more worthwhile, but we've already talked about a lot of this. I don't know if we talked about the last slide here. Let me see here. We already talked about all this before. Did we talk about the summary slide?
Yeah.
I think we did, but so I'll just mention it again. Logistics popular for K equal 2. LDA useful whenever you have very limited N. And Gaussian assumptions reasonable, so small sample numbers in Gaussian. And it's also more preferable when you have more than 2 classes. That's typically actually true because LDA it's preferable just to use logistic if you simply have binary, as long as they have a reasonable overlap. And then beyond then, you'll go ahead and spend the effort to put in LDA. Why is it more effort to put in LDA over logistic if you simply have a binary classification? Because that requires me, it's front-loaded. Remember I mentioned this, I have to calculate those density functions. I have to calculate pi and f. So the assumptions based upon that calculation require me to go through the whole data set and establish the function estimate. So that first process is very front-loaded. It's very front-heavy from a calculation standpoint. So I don't want to do that unless I have to. And anytime I attempt to make changes to or to adjust that system, I have to go and recalculate that value. So it can be very, very problematic to go and make adjustments to the distributions. Now, Bayes is useful whenever you have a lot of predictors, high predictor value, and as I said beforehand, LDA does have an upper cutoff depending on the distribution characteristics. Okay, we're going to start on 5. I didn't do a supplemental for you guys because I realized that what I was going to talk about would actually be better later on, so I will do a supplemental for you guys later on with that data because part of the talk that I gave on Friday to my to the group that I was working with, the freshman biomedical engineering students, dealt with brain data, so EEG, electroencephalogram, and some of the tools that I was utilizing are a little later on in this class period, so we're going to actually talk about it once we get up to doing PCA projections. So we did a little bit with LDA, but I want to talk about PCA first, and then I will give you guys a little bit of a direction that way. So let's talk about one of the things that we recognized early on in this class that I mentioned to you that I wanted to come back to, and that is data sampling in general is a big part of the way in which we process models and generate models. I can't necessarily explain it to you at a real a quantifiable level. I can't tell you specific metrics and methodology, but I can say that as you play with data in general, you begin to understand that the models themselves are actually they are to a degree or another a distillation of the data itself, right? The model is a consequence of the data it was trained with. It's not a separate thing. So we would say that it is a derivative process, but it's also like a set of cliff notes in a way. Now, think about it like this. If you have a set of cliff notes and you're reading a book, right, and you get a set of short notes, those short notes are based upon kind of key factors, extracting key information from that book. What happens with sort of overfitting perspectives is whenever you get too detailed notes, where you're literally just basically copying whole sections of the book, or you're using a pattern recognition methodology. You're saying, oh, okay, well, if you see this, and you see this, and you see this, then this is what happens in the book after that point in time, right? That's the consequence of a summary-driven approach. So models should be incentivized towards understanding the basic concept of telling a story, right, from a group of stories rather than memorizing a specific book. I don't know if you know this or not, or if you've ever watched a lot of TV with detective stories, but after you do it for a while, you begin to notice there's kind of a formula to it, right? Especially like the procedural dramas. You can kind of tend to notice maybe who the one that's responsible for it is, or you might be able to guess what piece of information that particular crime is going to be solved by, whatever else. That's a situation where you're developing a model to be able to understand a group of stories or a kind of concept as it works together. But as I said beforehand, if you're sitting there and you're watching the story again, right, and your brain can sort of pick out the exact elements of that system and say, I know the next step of the process, then it's pretty boring, right? If you know the end of the story, it's not really a mystery, it's not really exciting. When I look at this, I say, our models are built on what? They're built on data and access to information. So depending on which stories or movies or shows that I built for you guys to watch, right? What curated themes I gave to you would depend on how well you were able to model it. Which specific, some shows have a twist at the end, right? Anything by M. Night Shyamalan, it's obligated. He has a twist at the end of it, okay? Good movies, but whenever you go, he's just gonna throw this all out at the end of the movie in order to have some crazy plot twist at the end. You're just waiting for the plot twist, okay? That's where I say sometimes you can overfit to it. You can do the same thing too many times to the point where it becomes, essentially, it comes back around to being predictable. So we said, if I break the data up in one way, 70-30, we had our standardized test train split paradigm, there's really only so much we can do. Let's imagine that I picked a bunch of movies that had normal plot. Those are in the 70%. And then in the 30%, I have all the M. Night Shyamalan movies. Somehow they all got over there in the 30%, okay? You're gonna misclassify every single one of those because you didn't learn from it. You didn't watch them, right? You watched all these other movies and then somebody tells you the plot of Shyamalan movie and you go, what do you think the end was? You go, oh, I think this is the end of it. You go, no, totally wrong. You know, they were a swan the whole time. You know, it's a twist. But there's craziness to that where you go, if you get the wrong things in the test set and they're not represented within the training set, how can you ever learn that? You can't. There's a weird space that's possible with certain types of random selection that we could have gotten a bunch of sheep over here. We call them sheep and goats, okay? Sheep perform well. They follow each other, they herd together. Goats are cantankerous, right? They're going to butt their little heads against you and they're going to run away and you have to tie them up. So goats are over here. If you have a bunch of goats in the testing and you have all sheep in the training, how do you learn to manage goats? You don't. You can't learn to manage goats. You have to seed some goats in on both sides. You have to have even performances. Well, we can't guarantee it. Because if I decide which group you're in training or testing based upon some metric of your makeup, guess what? I bias the model. It needs to be random. It needs to be sorted and selected from a randomized initialization base, or else it's not truly representative of the underlying distribution of the system. So since certain distributions could potentially have asymmetric or uneven allocations of good versus bad samples or bad examples relative to the system, you could effectively learn a wrong version of the model or wrong information from one set of information that did not reflect well on the testing. In that case, what the testing is going to do is it's going to radically reflect an overestimation of the likely error that model would have if applied to the rest of, let's say, the rest of all movies, right? If you put it onto the IMDb database, right, the small movies that you trained on, the small movies you tested on, if you were to take your model of the normal movies, minus the Shyamalans, and you were to then apply that model to the rest of film in general, it would probably work far better than it actually did on your testing set. Say, well, that's terrible, that's bad. That means there's a high chance of even just asymmetry overestimating error. We don't like that asymmetry overestimating error. So we say that we're going to use methodologies for resampling. Matter of fact, sampling in and of itself is a type of resampling because you have what? You have the core real distribution. That's the actual population. Then you create a sample from that. That is a sampling methodology, okay? Then we have resampling, that is taking a sample from the sample or reordering it. So validation methodology is already a type of sampling with respect to the sample data. It's resampling. But we're going to utilize methodologies that are going to enable us to have different reference points for using different individual samples as both the training and the testing elements of the system, as well as keeping our validation set external. So these methods are actually formed from the training set and obtain new internal estimates of likely external error based upon treating individual samples or recreated samples based upon sort of a simulation paradigm to simulate what might happen had you gone to, so let's say you're walking through a neighborhood, right? And you come to one door, and then you skip 3 doors down and you go to the next door, right? That's your canvassing methodology for doing your survey, right? Please do the survey, right? So you walk down and you say, well, what happens, what's the theoretical universe where I step over 1 door to the right every time that I resample? Well, it should look very much the same because your initial random sampling methodology was designed to try to analyze the space. So by stepping over 1 step to the right and sampling every other house, then you should get something similar. So what we do is we're going to utilize a methodology we call the bootstrap to simulate the process of what would have happened had you gone and taken those samples if the underlying data set was in fact reflective of the real population. This is a weird one. I'll show you the reason why it's a weird one is because typically we don't do what we're going to do with the bootstrap. The bootstrap is resampling with replacement, meaning we're allowed to sample as the same sample more than once. The reason why I say the same sample more than once is because technically, if your seat next to you is empty, right, and I don't have anybody around you, but I know there could be somebody around you, and I say, well, I didn't take any samples, I'm just going to duplicate your sample over here and assume that someone close to you would be relatively adjacent with respect to their opinions and ideas, right? We've noted this because we are clustered together according to shirts, shirt colors and other preferences, including hairstyles. All right, so those ideas where we say the things that you prefer or the things you have general preference for should be reflected in your population adjacency. So if I resample you, if I clone you and take you as an additional sample, okay, now I've doubled you. Well, I want to keep the sample size the same. So I want to maintain n, right? But I want to be able to duplicate some samples to simulate the process of an alternative collection in which some samples were actually done more than once, higher density in a region with like priors, meaning that they had the same underlying populational density. And you just sampled somebody that was from that same group, in that area and you take the existing sample more than once, yes. We'll talk about it in a minute, but.
What you're describing, is SMODE a form of that?
Is what?
SMODE, where you oversample on a data set?
I think that does modal interpolation before resampling.
Okay.
I'll have to look and make sure. That one I'm actually not super familiar with, heard it beforehand with regard to a Novus, but I haven't worked with it much in general. We don't actually use Bootstrap for creating real data sets. We use Bootstrap for the analysis of a theoretical data set. This is the one where I go, what are you talking about? I create the theoretical data set to understand what the properties of the actual data set are. So by analyzing the possible worlds that could occur as a result of hundreds, if not thousands of resamples, I can actually understand the interdistributional characteristics of the original data set. So we're going to make a reflection of that based upon the alpha and standard deviation of a composite of many, many different bootstraps, being many different resample with replacement data sets. But first we're going to talk about K-fold or fold cross-validation methodologies, right? We say in general that the goal of system, I'm not going to go over this, I go over this constantly. Train, test, error, okay? We've seen this. Honestly, I look at this and I go, why does every chapter need to cover the exact same stuff again? There should be an assumption. But when I said to you, if we understand the baseline, we don't really need to go through it again. What do we see here? Bias variance dilemma, test train split, characteristic divergence, okay? We've seen that a million times. We've also even talked about this. Mathematical adjustments based upon characteristics of training error rate in order to make an assumption utilizing the test error rate characteristics, utilizing those information criteria to decide whether or not our holdouts are sufficiently descriptive. So we want to utilize a holdout to be able to evaluate the performance of the model as we say that the model's performance in the wild, right? That is whenever we release it to be able to start doing the job that we built it to do. So we build the machine and then we hook it up to the system. We want to try to test it first. And the only way we can test it is with data that has been, with sort of product, right? You have a shoelace tying machine and you want to test it. You've got to feed some cord in and let it tie some shoelaces first, okay? So this is a pump priming methodology where we test and make sure that the system actually does what we want it to do before we start tying it into the production systems of the real world. I typically tend to make a pretty big point of this in general, is that while this may seem a little boring, even inane, mundane, small data sets and small processes like this can lead to big problems in larger systems. So if you don't adequately test, you don't adequately verify functionality, you don't understand all the cases that can occur as a result of the way in which these models can interact with the real world, the real data they're working with, you can end up with something that can cause catastrophic problems, okay? Many of the bank failures and fintech stuff that's happened over the last few years have actually come from poor performance in modeling paradigms as a result. Please, guys. Second to last row, center. Okay, you need to talk, you've got hallway, it's fine. All right, so we say we have testing and we have a validation, right? Holdout. We keep it set aside. And the reason why we keep it set aside is what? I want to know what it does on totally unseen data. If it ever sees that data, if it ever even gets a whiff of what that data contains, it will attempt to try to adjust itself to characterize to that data, right? It's water. It is a mutable, flexible thing, right? It's going to try to take on the shape of its container, right? It's like silly putty. It's going to copy whatever you stick it to. So as a result of that characteristic, we got to make sure that we keep everybody separate. So how do we keep everybody separate, yet try to understand what might happen in testing so that we can avoid some of the biggest problems that we have? What's one of the biggest problems we have? Overfitting. When can we tell we've overfit? Only whenever the data that it can't see starts to perform differently than the data that it can see. So how do I stop the model from doing that overfit? How do I keep it honest while at the same time assessing that future performance? Well, the mechanism we're going to use is called the K-fold process. We already talked about validation, talked about autonomous splitting, and then we'll talk about it from this perspective. I already mentioned this beforehand. With respect to the validation approach, holding it out before, what can happen? Well, the validation set tends to overestimate the test error for a model trained on the entire data set. Now, why is that problematic? Well, we don't want to train a model on the entire data set because when we said we don't have anything to test it with. So if the testing set actually overestimates what would have happened had we trained it with all the data, that means that holding some of the data back actually makes the trained model slightly worse. So it's a loss, it's a cost. So by keeping some of the data back in order to test with in the future, we're going to lose some relative performance of the model because it doesn't have all the samples. Well, what do I mean? What am I talking about there? I'm saying that since it doesn't have enough total samples in the system, it's not capturing enough of the entropy. It doesn't see those strange shaped elements on the fringe of the system. So it can't fit to those odd characteristics, right? It can't watch every other kind of movie there is and then try to figure out a Shyamalan movie, right? Because it's just too different than the other ones. It has too many strange edges and weird twists at the end in order to be able to be characterized easily by the square and easily formulatable models of the previous system. So we say that if confusers are included in the testing set, then the system will overestimate if those confusers are lower likelihood samples in the system. So we're going to say that one widely used approach, and I'll talk about it, you guys will, I think, start to see the value of this as a result of the visualization of the discussion. But this, you open up my supplemental slides, because I think my supplemental slides do a far better job of describing. So this is all we get from the author slides, all right? But this is a better version of a analysis of k-fold validation. So it also includes a step in there that the author's slides don't include. So notice at the very top we have all data. This is our entire data set, the one we downloaded, okay? What's the first process we have to engage in order for model verification? The test train split, all right? I didn't actually ask you guys to do that as part of your as part of your process for your classifications, but some of you engaged in doing so, and I think that that's good.
The lab
right?
asked us to.
The lab asked you to, but I didn't ask you to do so with the, I didn't say emphatically you had to, but the lab does do the test train split. I think it's important because you can't really evaluate the model, but whenever we're doing strictly linear stuff, why is it not necessary? Well, because it's very hard for a line to overfit, okay? So when it's strictly linear, you don't have enough flexibility to worry about overfitting, all right? So that's the reason why I say linear discriminant, logistic regression, hardly are they going to perform poorly in the testing set. However, it's still good practice, and it will consistently maintain that practice going forward. So the k-fold methodology, we say k-folds. I'm going to keep with the sheep analogy for a minute, okay? Everybody knows what a sheep pen looks like, or for at least for the most part know what a sheep pen looks like. You've got a little pasture area, right? And you push your sheep into a little pasture area, and you don't want to have all the sheep together because they're kind of hard to deal with whenever they're one big group. So you've got your pasture here, and you push your sheep in from this side, right? And you might have a series of little pens put together around the outside of the space. And we call these little pens folds, right? A sheepfold, right? The sheepfold is what cuts them up into the groups. So as you push the herd inside of here, right, you're going to have some of them that are going to go off in this direction, and then you're going to close the gate off. You're going to have some of them go in here, and you're going to close that gate off, some in here, close that gate off, et cetera, et cetera. And you're going to end up with multiple folds that are equivalently sized little areas, little makeups of the original herd, right? So the original herd was out here. This is the whole population. We assume that if all of the sheep were equally distributed, right, randomly distributed into each of the folds, that each of these should effectively be a subsample, a random subsampling of the original herd, right? So that would mean that each fold is in fact a miniature representation of the original population. So I say, okay, how do I use that information? Well, knowing that I've done the same thing that I did initially with the data points, I start off with all data, and then I do my test train split, right? Then my training data, I'm gonna do this process. I'm going to apply the fold methodology. I'm gonna push my data off. Notice, the testing set, right? The test data over here on the right-hand side does not enter into the fold, all right? It's split off before, we split testing off over here before we ever enter the rest of the herd into the fold. The reason why is because of the fact that we want to have one fold, one group of the data that is unused by any of the previous processes, all right? But notice I've got some system that happens down here, right? Got some system that happens down here. Well, notice the coloring. Notice the symmetry of the coloring. What did I call the blue up there? The blue is test data, right? Then I created 5 folds from the training data. This is 5 equally distributed sub-samples of similar size. And at the first split characteristic, what have I done? That first fold, fold number 1 here, now this is testing, right? And the remainder of these guys are going to be training. Okay? And the next step of the process, well, 1 becomes part of the training again, right? So this integrates back into the training. And this one is the odd person out, right? This one's now test. So by stepping through the whole process, everybody gets to be a member of, with 5 population, end up with being 4 of them are going to be training, right? And then 1 is going to be left out as testing. This is testing for a local system. We said I wanted to be able to estimate the likely external local test data, right? So the external test data relative to the original process. I want to be able to estimate what's going to happen down here without ever looking at it. Well, since I can't use this data, guess what I'm going to have to do? I'm going to have to use some data within the system. But I said, well, if I pick the wrong data, if it's too small, if the fold's too small, and I pick the wrong data, then I'm going to be testing on entirely Shyamalan movies, okay? That's going to be terrible. It's possible, and it's going to be terrible if that happens. So, what do? I say, well, sometimes you're going to be the training, and sometimes you're going to be testing. Everybody gets to take turns. So this is a possibility that if we get a bad internal testing set, right, a bad internal evaluation, we're not stuck with it. It could either be part of the training set or part of the testing set. Now what I'm actually going to do here, this is the cool part about this, I'm actually going to train 5 models. Train 5 models. Each split, each version of the 4 samples that are used, or 4 folds that are used in the training, and the 1 fold that is used in the testing, right? Each one of those is going to be its own model with trained model and internal evaluation of testing performance. What happens with that? Well, we say, I can now attempt to pick whichever one works best. What did I say about the training and testing paradigm? I said that if I got bad samples in the testing, then I would have a poorly performing model. But if I got fewer samples that were in the training paradigm out of the global population by poor random selection, then I would have a model that didn't perform well in the general space because it didn't adequately capture the entropy of the system. So by shifting around such that everybody gets to be both training and testing with respect to the data sets, I get to play around with what could have happened with the way in which that data was sorted into testing and training. As I said previously, the models are a product of the data set they're trained with. Each of these models will actually be slightly different in terms of their parameters and coefficients because the data that they were trained on was slightly different in each case. Also, since the internal testing was slightly different, if they perform well on their internal training and their internal testing, the likelihood is they will actually outperform even their own internal testing when applied to the global test data. All right? We'll continue on from here, but I want you guys to think about the impact this has. If I now have 5 different models to select from, now I can be able to pick the best one, the one that performed best on the data as it was sorted out of the system, such that I can attempt to try to maximize the end case test performance for the global testing set. So we'll keep talking about this, and then we'll move on to the subsampling methodologies. And for confirmation again, our exam is not going to be this Friday, but next Friday, okay? So if anybody wasn't here last week, I adjusted, it is going to be Friday of week 9. I will put a post on that on campus so everybody's clear on it. So we'll get through chapter 5 before we get there and probably have one more full homework and lab. Thank you.